Hello and welcome to today's lesson on forces in motion, which is part of the forces topic in GCSE Combined Science Physics. So in today's lesson we're going to look at linking Newton's laws of motion to movement. So if we've been successful and learnt in this lesson, we should be able to understand how to calculate a resultant force, link resultant forces into the acceleration of objects, and derive values for an object based on Newton's laws of motion, which links into the following part of the GCSE Combined Science Physics Specification: 6.5.4.2.1 Newton's first law, 6.5.4.2.2 Newton's second law, and finally 6.5.4.2.3 Newton's third law. Now, understanding if an object has a resultant force acting on it will allow you to understand the motion that object will make. So for example, let's consider a Formula 1 car. Now there are two forces acting on the car. There's thrust going with motion and friction and air resistance going against the motion, which you can see in the following diagram. So you can see the thrust acting with the motion and the friction air resistance acting against the motion. Now this particular diagram is called a free body diagram, and this shows the forces on an object. Now just to clarify, this does not show all of the forces on the object, because we also have weight acting down from the center of mass and the reaction force acting upwards, as shown here. Now in this example we're not going to consider weight and reaction, as vertical forces do not affect horizontal motion, and we're only going to consider the horizontal motion of the car. Now, off the starting grid, the thrust of a Formula 1 car is much bigger than the air resistance produced. So this tells us there's a resultant force forwards with the motion, and this makes the car accelerate forwards. Now as a note, the air resistance is very small, as very few air particles are being moved out of the way by the car every second, because the car is not travelling very fast. So what happens is, as the car then speeds up, the air resistance acting on the car increases. Now the air resistance increases as when the car moves faster, more air particles are moved out of the way every second by the car, so this increases the size of our air resistance. So now the resultant or overall force is lower, because the air resistance and thrust are more similar in size now, so therefore the difference between the forces is smaller, so the acceleration is therefore going to be smaller. Now the air resistance will get larger and larger as more and more air particles are pushed out of the way every second, as the car moves faster and faster and faster. Now this means eventually the air resistance will be the same size as the thrust force of the engine. Now when this happens, this means that there's no resultant force, because the two forces are the same size but are acting in opposite directions, so will cancel each other out. Now as a resultant force causes an acceleration, no resultant force leads to no acceleration. So this means our car cannot travel any faster. Now this is called the maximum possible speed. Now if this object was falling, we will call this the terminal velocity. So for a falling object, the maximum possible speed is the terminal velocity, but for a moving object such as a car, we will call it the maximum velocity. Now there are two forces acting on a moving object: thrust, which acts with motion, and friction/air resistance, which acts against motion. Now at the start of the journey, the thrust is larger than the air resistance, and this produces a resultant force and acceleration forwards. Now as the speed increases, the air resistance increases until the air resistance equals the thrust. This produces no resultant force and no acceleration. So this gives all objects a maximum possible moving speed. So for falling objects, this is called the terminal velocity. So to assess our understanding of this concept, let's consider a ball falling through a tube of cooking oil. So a ball will be dropped in the tube of cooking oil, and the ball will fall through the oil down to the bottom of the tube, and we can predict the motion of the falling ball by using Newton's laws of motion. So what are our forces on the ball as it falls in the oil? Well, we have two forces. We have the weight acting downwards and the friction acting against the motion. Now if you are measuring the time taken for the ball to drop, how can you gain the most accurate time? Well, to gain the most accurate value possible, possible, the largest possible measurement must be taken. So to get the most accurate result, the time measured must be the largest, so it must be dropped from a higher distance. Now let's describe the motion of the ball at the start of the journey. Well, at the start of the journey, the ball will accelerate downwards. Why is this? Well, it's because the weight acting downwards is much larger than the friction acting against the motion. There's a resultant force downwards, it will accelerate downwards. Now, as the ball continues its journey, what's going to happen to the motion of the ball? Well, eventually the ball will stop accelerating because the weight acting downwards will be the same size as the friction acting against the motion. So eventually friction will equal weight. This means there's no resultant force, so no acceleration. Now, why does the friction increase as the ball travels further down the tube? Well, the friction increases as when the ball moves down the tube, it increases in speed. So when the speed of the object increases, the object moves more particles out of the way every second, which will increase the friction. Now, eventually, what happens to the size of friction and weight? Well, after a prolonged period of time, the weight and the friction equal each other, but it does take quite a while for this to take place. So at this point, what happens to the speed of the falling ball? Well, as there's no resultant force on the ball, there's no acceleration. So this means the ball remains at the same speed. But why will our ball keep moving even though the forces are balanced? It's because the ball is not accelerating. A resultant force causes acceleration. No resultant force, no acceleration. So the ball will maintain its constant speed. Now, this phenomena in physics is called inertia. So the ball will want to remain at the same speed when there's no resultant force acting on it. It has inertia. Now, in this case, what's the name for the maximum speed achieved by the ball? Well, the maximum speed is called the terminal velocity, but this is only suitable for objects falling when the thrust is provided by gravity. So what have we learned about when we've considered forces in motion? Well, a number of forces acting on an object may be replaced by a single force that has the same effect as all the original forces acting together. This single force is called the resultant force. Now, Newton's first law is that if the resultant force acting on an object is zero and the object is stationary, the object will remain stationary. But if the object is moving, the object continues to move at the same speed in the same direction. So the object continues to move at the same velocity. So when a vehicle travels at steady speed, the resistive forces balance the driving force. So the velocity of an object will only change if a resultant force is acting on the object. Now, you should be able to apply Newton's first law to explain the motion of objects moving with a uniform velocity and when objects where the speed and direction changes. Now, the tendency of objects to continue in their state of rest or of uniform motion is called inertia. Now, Newton's second law is that the acceleration of an object is proportional to the resultant force acting on the object and inversely proportional to the mass of the object. So as an equation, the resultant force is equal to mass times by acceleration. Now, you should be able to explain that inertial mass, which is the mass found in this equation, is a measure of how difficult it is to change the velocity of an object. So it's defined as the ratio of the force over the acceleration. Now, Newton's third law is that whenever two objects interact, the force they exert on each other are equal and opposite, and you should be able to apply Newton's third law to examples of equilibrium situations. So if you've been successful and learnt in this lesson, you should be able to understand how to calculate a resultant force, link resultant forces into the acceleration of objects, and finally derive values for an object based on Newton's laws of motion. So I hope you've enjoyed today's lesson on forces in motion, which is part of the GCSE Combined Science topic of forces. Thank you very much for watching and have a lovely day.